Riley, you sent me an email that I didn't, yesterday was kind of a crazy day for me in the afternoon. What was exactly was your email again? You said something about the homework wasn't correct, or you should say incomplete.
The question 11 just cuts off, and I didn't know if you want to.
Question 11 cuts it off. That was my master plan. Question.
It's like part C, but it just doesn't have it.
Okay, which one is question 11 again?
It's on page 2.
245.
283. It should be the first. We're technically number 4.
Oh, number 4. Yeah, that's okay. Number 4 on 283. Yes. So in other words, why don't you stop at do part B, A and B, and then just stop after that. Okay. I think that was a mistake on my part, but I don't have that with me. So just stop there. Yes, I apologize for that. Okay, so what are the two types of collisions we have? Elastic and inelastic. What is conserved for both of these collisions? Linear momentum. So when you see something like this, linear momentum is conserved for both of these. So P initial, P final, and P initial, P final. They both do. But what does elastic collisions conserve that inelastic does not? Kinetic energy. So these right here are going to have KE initial equals KE final. Like that. Okay. And then we took a special case of 1D elastic collisions. And you can just use both of these two, and that'll be perfectly fine. There's nothing wrong with that. But why is that a little more mathematically challenging?
Because of squares.
Yeah, because this will give you a linear equation. You have to put that into the kinetic energy, which has that v squared. And then you end up with a quadratic equation you have to solve. So there's a lot more opportunity to screw up the math. So what we did is we took this expression here, for this case here, we beat on it, and we ended up with a really neat relationship. And what was that?
Relative velocity initially equals relative velocity.
Put in one more thing. A minus. The relative velocity flips. So what we found is that you could take this condition and this condition, and you could come up with the easier condition that v relative initial equals minus v relative final. Like that. Okay? And what does that mean? That means if I'm in a 1D collision with somebody, if I see somebody coming at me at 5 meters a second before the collision, what will I see after the collision? I'm going to see them moving away from me at minus 5 meters a second. That's what that means. Okay? And again, when is that valid? Only when you have to have a 1D elastic collision. If you try to apply that in, for instance, if you look at your homework, which is due when? Friday? If you try to apply this to equation 88, if you look at that back sheet, there's problem number 88, which we're going to be doing. You have an elastic collision between a bowling ball and a pin. They tell you that it's elastic. Can you use that equation there? Because what kind of collision is this? A 2D collision. So you're not going to be able to do that. Number 8 is going to involve some really kind of fancy, some good algebra for you, along with a couple of these other ones. The algebra is going to be actually will be good for you, make you strong. Okay, does that make sense? So let's go through, and I want to continue with this. And again, this is called Newton's cradle. So Newton's cradle exists. I always call it the dumb executive game, because it seems like if you become an executive, you have to have one of these things on your desk, or you ain't an executive. Okay, so let's go through and figure this out. So if I have this, let's go through and do all the pieces here. So if you look on your test, okay, hey, part 2, number 2. It looks almost like we have some of this, something like this, except it's the masses are different. So in a case like that, so in this case here, we're going to have the equal mass case like that. I want you to go through and figure out the physics of what's going on with this. I'll stop that because I can see it's pretty quick. So we have this here. This is M1. This is M2. This is initially at rest. And this is some height here, H. And this is initially at rest. Okay, I want you to go through and analyze this whole thing here. So what is the final height of M2 if M1 equals M2? Okay, now what is it going to be? 8. But let's go through and actually work it out explicitly. So I'll give you a hint, there are 3 parts of the physics here. What are the 3 parts of the physics?
Collision.
Okay, let me, there is a collision. Good. Let me rephrase this. Put them in order, the 3 parts of the physics here. That's not the first part. What's the first part? That's not the first part. Yeah, what does this mass have to do first? It has to move down here so it can collide. So the first part of the physics here is what? You have this mass here. I'll just call this, I'll say M1 equals M. And this is going to go down to here. And this is going to have some velocity like that. And this is H. So if I want the velocity of this mass when it gets to the bottom, what's the physics here? No? Okay, it would be circular motion, but tell me why that's not going to help us. What am I not asking for?
You're not asking for a force.
Yeah, if I already asked for the tension here, then circular motion. But there's another part to the physics as well, even if you did the circular motion.
Is it like the Tarzan problem?
So it is a Tarzan problem. So is the physics there? Except we're not doing the circular motion. I mean, we're not doing the circular motion. But how do we go from here to here?
Conservation.
No.
Conservation of energy.
Why is it conservation of energy? That's correct. Okay. So when you do this, you're going to have to say E initial equals E final. Am I going off the edge here? I'm not yet. Sounds like a metaphysical statement. Am I off the edge? I like metaphysics. Okay, so proceed. So why would we say E initial equals E final? When can we say that? When the non-conservative work equals 0. Are there any non-conservative forces in this problem? Yes. What is it? Tension. But why does tension, which is a non-conservative force, do no non-conservative work?
Because it's perpendicular to the direction of motion.
Perfect. Just tinker with that ever so slightly. When this moves a tiny little, so this right here is the tension. When that moves some tiny little distance to here, that tiny little displacement here is perpendicular to the tension. So if you look at it from tiny little displacement to tiny little displacement, the T is always perpendicular to the tiny little displacement. So therefore the work is 0. So you can say, since the non-conservative work equals change in E, and this is 0, I can say that E initial equals E final. Okay. What's another way? I told you when you have a conservation problem, often what are you going to have?
Final.
Before and after pictures. Okay. So you see before a picture, you think an after picture, you think conservation law. Okay. Now, when would you think conservation of linear momentum? When what happens? A collision. You see a collision, you think conservation of linear momentum. You see something moving from one position to another position, you think conservation of energy. That makes sense? Hey, you have a test on Thursday, frequently called Monday, and the limit that Thursday basically quantum mechanically tunnels through the weekend to Monday. Okay, so sorry about that. I've been up since 2. I don't recommend it actually. I don't recommend it at all. So go through and tell me how you do this, because you know exactly how to do this. Energy is what?
Kinetic energy plus potential energy.
Okay, so we have K initial equals U initial equals K final plus U. Okay, what is your initial kinetic energy?
Zero.
Because
There's no plus.
the system's at rest, or a little mass is at rest. Plus,
Energy.
what is my potential energy? That's true, and if you do that, and I would put that into there too. Where are you taking the ground to be? Yeah, taking the bottom. Suppose you're working with your buddy, and your buddy says, no, the initial potential energy is 0. What is your buddy doing? They're taking the H equals 0 line to be here. Now, I would do the exact same thing that you said. So I would take this to be my H equals 0 line. And then this is the distance above the ground, so this is my MGH. Equals. What is your final kinetic energy?
1/2 of the square.
Because,
Max is always-
well, that's because kinetic energy is always 1/2 mv squared. If you have no clue what kinetic energy is, you always write down 1/2 mv squared because that's what it is. Then your potential energy,
0.
plus 0. Okay, your masses go out, I'll take over the 2 square root, and Shazam, I get my V as 2GH. So that's the first part of the physics. So when you look at question 2, number 2, on part 2, number 2, part A is going to be a conservation of energy problem. Okay? What's the second part of the physics now? Now this mass now is here. It has a velocity like this V. What happens now?
Momentum,
Put another one in front of it.
linear,
Put another one in front of it.
conservation of linear.
Conservation of linear momentum. So this part here. So for part 2 of this. You're gonna have P initial, it's P one. So your picture is this. Here's your M1, which is M, it has a velocity here, V. Here's your other mass here, M2, is M1, which is also M. This is at rest. And then what do they do? This one's gonna have some velocity V1 final, and this one's gonna have some velocity V2 final. This is your before picture. This is your after picture. Now, I've seen this before. We saw yesterday. What should be the velocity of what should be V2 final? What should be V1 final? But we're going to work it out again.
E1 final should be 0.
0 and it's going to be positive with that value. So basically, this one's going to, if we do it right, this one is going to actually be at rest. This one isn't going to be moving. Okay? You can see that actually when you do this. So look, just as this one hits here, look at the motion of this one after the collision. So if I go and catch this here, right? And see that one's at rest. Right? So like that one's at rest. At rest. That's how that works. So let's go through and do it though. Okay, you tell me how to do it. Okay, so I'm going to say P initial X equals P final X. What is P initial X in this case?
MV.
So it's going to be this mass times this. I'm going to put in a plus 0 just to be pedantic because you have to look at the whole system and this one's not moving. So that's just to be pedantic. Okay, what is your final momentum of the system?
0 to 72 V2.
We don't know the 0 part. We need to prove that. I mean, what you said is true, but we don't know that ahead of time.
So M1 to V1 plus M2 V2.
And I'm just going to put finals in there and that's fine. So I'm going to take the momentum of this guy here. And then the momentum of this guy here. Does that make sense? one nice thing happens,
That's enough.
all the masses cancel. Okay, so this is one equation. Is there another equation? Since it's an elastic 1D collision.
We can use the velocity is relative and.
Now you could do the kinetic energy, but again, it's not wrong to do the kinetic energy, but it's a first class pain in the rear. It's going to be a lot easier to do that V relative initial equals minus V relative final. I'm going to say V relative initial equals minus V relative final. So how do we define the relative velocity? What minus what? Well, it's V1 minus
V2.
V2, but I thought it was V2 minus V1.
Doesn't matter as long as you use the same.
Yeah, it doesn't matter how you define that term, just as long as you define it on the left and on the right as being the same. As long as you do the same thing, you do 1 minus 1, 1 minus 2, or 2 minus 1, it doesn't matter. Just do the same thing to both sides. Okay, so we're normally doing 1 minus 2. So what does that give me then? V1 is? V1 is our friend here, V. Minus V2 is 0. Equals minus, what do we have on this side then? So this will be V1 final, then minus V2 final. If we distribute through the minus sign, then I get that. Okay, how do I solve those?
And
I would just add them. Again, you could solve for one, substitute the other. In this case here, it's just going to be easy to add them. V equals V1 final, it's V2 final. This is V equals minus V1 final, it's V2 final. I'll add these, what does that give me?
0.
Okay, so I get 0 here plus 2 V2 final. This side, 2V. 2V or not 2V, that is a question. That's what that's actually a metaphor for. Hamlet, that whole soliloquy, is actually for basically it's a metaphor for 1D elastic collisions. That's what that's really referring to. That's why people didn't quite understand it. He was so advanced. Okay, so then what happens here? The 2 goes out. This tells me that V2 final is not that. This is V. So what does it mean then about V1 initial? I mean V1 final?
0.
Yeah, if I take that and put it in here, that gives me 0. Or if I put it up here. So if I substitute that back in, I'll just rip this one here. So therefore, V1 final is 0. And we see that. That's exactly what happens in this collision here. These have equal mass or more or less equal mass. You can see it goes just like that. Okay. Now, what's the third step of the physics then? So if you look on your little example here, in your part B, question 2 and part 2, number B, what are you going to do for this part here? It's basically going to be this calculation here. But again, the masses are different, so the masses aren't going to cancel. Okay, what's the third part of the physics? Okay, so the third part is going to be, we'll put this over here. We now have this one. Here's our M2 equals M. Now this is V. The question is H max equals. Okay, so what's the physics here? Another conservation of energy question. So the physics in part 3 is the initial equals V4. Again, your initial equals the final. This is your initial kinetic. It's initial potential equals final kinetic. Final potential. What is your initial kinetic?
V squared.
1 times V squared. Your initial potential. because you're taking the ground here to be 0. What is your final kinetic energy and why?
0.
Why?
So it's like a point of rest before it falls back down.
Because what are we looking for?
The maximum height.
Maximum height. So what's going to happen is it goes up, it slows up, slows up, slows up, stops momentarily. Then what happens? It starts coming back down. So where it stopped, that's where you're going to have maximum height. So the velocity at this point would be at the max 0. Okay. So this would be 0 plus, and then your U final is mg, which I'm calling this H max here. So this is your mg H max. Okay, so your m's go out. This gives me 1/2 v squared equals g H max. We have our velocity here. Hail Mary pass into here. We got 1/2 2gh. The square root kills the square root. GH max. 2's go out, G's go out, H max equals H. Okay. And that explains the game. Well, the setup. That's entirely how that works. Now, what would happen? Explain this one now. Explain how that one works. Yep.
You change the masses, so.
All the masses are the same.
More, like, it'd be 2m instead of.
No. Okay. What does this one have? It's the first one. And what happens in that case? So when you have a whole chain of these things. You know, if I were a spy, and if you wanted to ever get information out of me, all you'd have to do is just make some like real irritating noise, and I'll tell you anything you want to know. I'll even tell you things you don't want to know. Just make the noise stop. Whatever you do, please make it stop. We have this. Okay, these are all the same mass. So what happens here? This one swings down, glides elastically with this one. And again, why is it approximately elastic?
Steel balls.
Yeah, if I had marshmallows here like this, no, it's not going to work very well. But with steel balls, what happens is very little deformation in any of the collisions. There's obviously noise, so you're losing a little bit to sound waves. You're getting some vibrations. You're losing a lot to vibrations. But for the most part, it's not a bad approximation to say it's elastic. So this comes down here. In the first collision, what happens? What did we show? What happens if you have an elastic collision between equal mass objects, where one of them is at rest? I just worked it out. So this is it. These are all at rest. If you look at the first collision here, what's going to happen? That comes down here like this, has a velocity here, v. You have all these other ones. 4 of them. This does an elastic 1D collision here, and then what happens? This one is now at rest. And now this one has a net velocity here, v. And 5 volts. Okay, then what happens here? Elastic 1D collision. So now what happens is that these are at rest. Now this one has a velocity v. And you have this, and these are at rest. And then the same thing happens in kind of a daisy chain fashion. And that's why it just goes back and forth like this. That makes sense? You have elastic collisions basically Elastic collision, so this is at rest, so this is moving, elastic collision, now this is at rest, this is moving, elastic collision, now this is at rest, this is moving, elastic collision, now this is moving, this is at rest, this is moving up, comes back down, and then starts the whole thing the other way. Pretty simple. Questions? What happens if I have two? Yeah. Why is that happening? It's basically the same thing, except what's happening now. The effective mass of this guy is basically kind of 2L. So what's going to happen by conservation of linear momentum and energy, you're going to have then two going up like this as well. Okay. Questions? Okay, now I'm going to impart the rest of my pool knowledge. So the first part of the pool knowledge was the cue balls, right? If you have two, if you have a cue ball and just a regular billiard ball, they have the same mass. This is at rest. Head-on collision, what happens? This one's at rest, and then this one moves with velocity v. That's what we've been doing here. Here's the other part of my pool knowledge. There's a part of me that doesn't want to do this because people use this result, but you have to remember where it's going to be valid. It's only valid in a very, very specific case. So consider two equal mass balls. Where one ball is at rest. The balls make the moving ball makes a glancing collision with the ball at rest. What does glancing collision mean? Is it head on? No. So it's not head on, it's going to be like this. That's glancing. This is head on, this is glancing, or this is glancing. So it's meaning not head on. If the collision is elastic, what is the angle between the two balls after the collision? Let's draw that picture. Now here's one ball, mass m, velocity v naught. Here's the other ball here, mass m. This is at rest. This is before. And after the collision, they make a glancing collision. So this one goes off like this. On this v1, and this one here goes off like so. This is the first ball. This is the second ball. Here's the first ball. Here's the second ball. This is the velocity of v2. The question is, what is that angle? Now it's going to be a nice little result. But again, when can you apply this result? This is why you do derivations, because you have to know when a valid result is valid. This result we're going to get is going to be only valid if there's three things we need. What are they?
Indirect contact.
Okay, well, it's a collision, so sure. What are the stipulations in this problem? What do you know about the masses of the two objects?
Equal.
They have to be equal. What does one of the masses have to be? At rest. What kind of collision does it have to be? elastic. You have to have those three conditions. Otherwise, this result won't work. So this result here, when you get this result, are you going to be able to apply it to that question 88 in the back here, where you have the bowling ball and the pin that's making an elastic collision? Can you use this result we're going to get? No, because they have different losses. Okay, so you can't do that. Okay, does anyone know what the answer is? Does anyone played enough pool to know what this answer is? It's gonna be 90 degrees. Okay, so the theta, so the answer is theta is gonna be 90 degrees. There is one other stipulation. We're neglecting English on this. Okay, what's it when you play pool? What is English? It's a spin. Okay, if you put in spin, you can make these do whatever. I mean, if you know what you're doing with it, you can make these do pretty much anything you want. The spin, the complication from spin is phenomenal. It's not one bit obvious. Okay, so no English in this. Okay, I think you're pros at this. You tell me what to do. What? Yes. Okay, so we have P initial equals P final. Can I say, and obviously by the way I'm writing it, I can't. MV naught equals MV1 plus MV2. Can I say that? How come? What would this treat the momentum as? More? It's as a scalar. So you can't do this, isn't fundamentally wrong. This treats P as a scalar. Okay, what little thing can I do to that equation and then have it correct?
You need your vector arrows.
So you need those vector arrows on it. Okay. So I can say this is completely true. That's good. That'll work. Okay. So we have that equation, and we're going to go about doing. And normally, what do we do with this? When you have this, what do? We break it into X and Y components. This one we're not going to, because it turns out there's going to be an absolutely beautiful way to actually solve this. And I want you to see it, because sometimes you have to do this. Okay, what's the other piece of the physics? So what are you going to say? It's an elastic collision. What's true in elastic collisions? The kinetic energy is conserved. So I can say, hey, the initial. You can state my final. So what does that become? The initial kinetic energy is 1/2 m the v naught squared plus 0 equals
1/2 40 squared.
v1 squared plus
V2 squared.
what's nice about this equation?
Some yams gone.
Yeah, all the half and m's go out. These are the same, so this gives me v naught squared, v1 squared plus v2 squared. Okay. Now, I want to show you another way to do this. So instead of breaking P1 initial equals P final initial into X and Y components. Let's draw the vector picture, vector addition picture of this. Okay. I'm going to say here. We have this. So this right here, this is our initial momentum. This is just going to be the P initial. I just call it P0. What does that have to equal? This is going to have to equal the momentum of the first particle plus the momentum of the final particle. So this picture right here, this is this guy. That's this. And what is this? This guy here, P1. This guy here, P2. This angle here is there. So let's draw this. So this is what I'm calling P0. Okay. So if I were to draw this as a vector, what does it look like? Don't overthink it. Yeah, that's easy. This right here is going to be my P initial, which I'm calling this P0, and this is just going to be MV naught. Done. That's pretty simple. Hey, how do I look at these? Yeah, I take this vector here. This is my P1. I'm starting off of that for no good reason. And then I take the tail of this fellow and add it to the head of that fellow. And this is P final. Oh, I'm sorry, this is P2. And your P final goes from where to where?
The tail of
The tail here to.
you want to
Exactly, this is my P final. Hey, but what does P final also have to equal? P initial, which is my P naught. So I really have what I have here. Is this. I have my P1, which is MV1, added to my P2 here, which is MV2. And here's my P initial here, which is MV naught. Now here's the tricky thing. Where's theta in that picture? So this theta here is the angle between these two vectors. Where is that in the picture? Everyone agrees with this?
Yeah.
Tell me what's not. Let's think about this a little bit. It's going to be obvious once I point it out. Okay, what is this? This is the angle between these two vectors. So, right, so P1 goes this way. P2 goes this way. So if P1 were to go this way, this angle right here, that is my theta. So what is this angle here?
180 minus theta.
This is 180 minus theta. Hey, what does that look like from, okay, it used to be 11th grade in high school. That's our buddy. And one time you had to drive this in New York State, but they got rid of that. But we've raised standards. You had to be able to do it for the regionals. The law of cosines. That's right, the law of cosines. Excellent. Okay. This is the law of cosines. All right, so here's theta C A B. The law of cosines. What is the law of cosines again? Give me a hint, there is an equal sign. It's like I gave it away. C squared. That's excellent. C squared, it goes over here.
So a squared plus b squared.
There is a cosine. Comes with a minus sign. Almost 2AB. Okay. So what do we have here? What is A, what is B, and what is C in that picture? Let's start off with C. In that picture here, what is C?
B2.
No,
No, it's,
I agree, no. I agree with that next statement that says it's.
yeah,
Okay, C is opposite the angle.
and P equals MB.
Yeah, so this right here, here's our angle, this right here is our C. This is our C. It doesn't matter which one we call A or B? No. I'll call this one A here and I'll call this one B here for no good reason. So what do we have here? We have this M, V naught here, comes in squared, equals this M, V1 squared, plus M, V2 squared, then minus 2 M, V1, M, V2, cosine of what?
180 minus theta.
180 minus theta. Okay. One nice thing cancels.
Half squared.
Yeah, I have a M squared, M squared, M squared, M squared, all the M squareds go out. So this gives me V naught squared equals V1 squared plus V2 squared minus 2V1 V2. Okay, I'm just leaving it like this for a second. Cosine of 180 minus theta. Oh, now we get a beautiful thing happening here. What beautiful thing happens here? You have your hint, it's on the board. With a box around it. From the elastic condition, we know that V naught squared equals V1 plus V2. So this term here cancels this term here. So that term cancels the sum of those two here by this equation here. Pretty slick. So this gives 0 equals minus 2V1, V2, cosine of 180 minus theta. I can divide through by the 2, the minus sign, the 2, the V1 and V2, because they're not 0. I can divide through by this. This gives me this. What is the cosine of 180 minus theta? If you cosine and shift it by 180 degrees, what do you get? You get a minus cosine. Get rid of the minus sign here. So you get cosine of theta equals 0. When is a cosine equal to 0? When the angle is 90 degrees. So therefore, theta is 90 degrees. There, I have imparted all my wisdom of pool. They're the only two things I know about pool. Pretty slick. Now, when can you use this result? Only when, what are the conditions?
When elastic collision.
Elastic collision. Same mass, and one has to be rest. Hey, let's look at this thing called practice test. Well, let's look at part 1, number 6. Let's read it. Consider 2 equal mass pool balls shown below. That's interesting. The first pool ball, initially traveling to the right at 10, slides elastically. The second, or initially, at rest. That was interesting. What is angle theta and the velocity v of the ball shown below after the collision? So, this one here. Question is, what is that theta? Now, I got just a lot of crazy things when I gave this before. You tell me what to do with it.
90 minus 36,
Done! Why?
because that whole angle has to add up to 90,
Because,
because we just proved it.
yeah, because we have two equal masses, one's at rest, elastic collision. So this theta here has to be 90 minus 36.87 degrees. You work that out. Now tell me then, this is some velocity v. Now tell me how to find the velocity v, and there's different ways to do this.
Conservation of kinetic energy.
That's what I would do. Okay, I would say conservation of kinetic energy. I'd say KE initial. Has to equal KE final. And then this one here, I think I give you. I'll tell you that this is 8. I'll call this one V2. Call that one, we'll just call that V. That's 1/2 m V2 squared. 1/2 m's go out. So this gives you 10 squared equals V squared plus 8 squared. So this is 36 equals V squared, or V equals 6. What's another way you could do this? That's the easiest. I mean, equally easy way. Well, not quite equally easy.
Conservation.
And what would you have to do with the components?
Break to X and Y.
Breaking up into X and Y components. So another way you could easily do this is I could say P initial X equals P final X. Does that make sense? If I were to do it this way, what would I have? P initial X is what?
And
M times 10. What is P final X? What's the X momentum of my buddy here?
8.
It's going to be M times 8
this,
cosine of this 36.87 plus
and
M
And V1.
times this V1 or V or whatever I'm calling it, V times
Cosine theta.
this cosine of the theta. So it's going to be this guy here goes into there. Then you just solve the V1. You could also do
Conservation of energy.
just did that. We're doing about conservation of linear momentum. Since it's a vector,
y.
you could also do the Y. I could do P initial Y equals P final Y. That make sense? Okay, what would that one give you? You know, I guess technically hot down. I go like this. We still have some time, but I guess that's requires gymnastics. Have a good day.